Voilà, c'est mieux. On est là.
Okay, should I start?
Oh, yes.
Okay. So good morning, everyone, or good day if you're in another time zone. Okay, so today we will be focused on comparison geometry again, but last time we explained how to do comparison geometry when you have upper sectional curvature bound. So when you have a non-positive sectional curvature, that's the case where we did the proofs and so on. Here we will see what's going on when you have lower curvature bound, but not on the sectional curvature. There is a well-developed and rich theory for manifold with non-negative sectional curvature, but we will, and at first glance, so the first steps are quite similar to what we did yesterday for non-negative sectional curvature, though it goes in completely different directions afterwards. But to give another perspective, and also as a teaser for Andrea Mondino course next week, we will focus on lower bounds on the Ricci curvature. We could use so we could use the equation that we used yesterday on the derivative of the Hessian of the distance function. Sorry. This one. Yep. It would actually give quite a lot of information, but we will derive our main tool using another root, which is a very important thing in the study of non-negative Ricci curvature, which is sometimes called the Bochner formula. So a lot of stuff are called Bochner formula, but maybe that's the simplest one. So and this one is maybe the one which is the easiest to state, because you only need to understand function. HM or HN? Where? Hessian, yeah, sorry. Thank you for the question. Okay, so the Bochner formula has this advantage that it's yeah, so you're using very simple function. So let f from a Riemannian manifold M to R be a smooth function, then it tells you how to compute the Laplacian of the gradient of any function, or gradient squared, but you can get the Laplacian of the gradient afterwards if you want. So, and this is given by the following formula. So you have the Hessian of f squared plus the inner product of the gradient and the gradient of the Laplacian So, and this formula, as I write it here, would be true in Rn. It's just like commuting partial derivatives. You can do a sanity check in Rn as an exercise. But when you're on a manifold, so higher derivatives don't commute anymore. And because you have computing third derivatives, and that's where curvature enters. And so you get an extra term with where the Ricci curvature appears. Here. The proof is just a computation. I won't do it. It's just like commuting partial covariant derivatives to make the curvature appear and trying to identify all the terms that appear. So what does it give us? So you can use that for a lot of stuff. You can prove like eigenvalue estimates. So the thing compared to the fundamental equation that we dealt with yesterday, the thing is that this was only for the distance function, whereas this Bochner formula applied to any function. Well, we will get a lot of information by applying it to distance functions, and actually they are closely related in that setting. But yeah, so this is a more general tool, and actually this is also a first step towards defining Ricci curvature bounds on metric spaces, because all this involves here is calculus on functions, and calculus on functions on metric spaces can be derived with a lot of work, but you can make sense of a lot of those things here. The Hessian term will be a little problematic, but there is a way to circumvent that, to get rid of this Hessian. Okay. So now let's apply the Bochner formula to a distance function. What does it tell us? From M, or some open set in M, actually. Yeah, maybe let's make that clear. We don't need... This is a purely local computation, so having a function defined on the whole of M or on an open set in M doesn't make any difference. So what do we get? The thing is that this, maybe I should be clear that my Laplacian is a so-called analyst Laplacian, so it has negative eigenvalue, which is just the sum of the second derivative in every direction in Rn. So I know there are competing conventions, so we have to be careful with that. Okay. So if we have a distance function, its gradient is constant in length, has constant length. So this term will give 0 here. And here we will have Hessian of R squared plus, well, how can we write that? So gradient R is just the radial vector field associated with the distance function. And so del R inner product gradient of Laplace R will be just the radial derivative of the Laplacian of R, and plus then Ricci of gradient R. Okay. Now, what should we do then? Maybe just a little interpretation. So this is actually, this is what you would get when you take the trace of the fundamental equation. So we could have gone with the fundamental equation for the Hessian of the distance function. Okay, and so we had noticed that the derivative of the Hessian of the distance function was controlled by the sectional curvature, and it told us that the second fundamental form of the level set of the distance of the distance hypersurfaces evolved as with respect to a certain PD involving the curvature. And here, so the fundamental equation said that evolution of the second fundamental form of R equal constant is controlled by K, the sectional curvature. And here, when we trace it, actually, what we get is that evolution of the mean curvature of those hypersurfaces is controlled by the Ricci curvature. So the Ricci curvature controls the evolution of the mean curvature of distance hypersurfaces, which are sometimes called equidistance. Okay. Now let's try to get something more manageable by assuming that we have a lower bound on the sectional curvature. Okay. So, yeah, maybe first note the following. So, you can see the Laplacian of R as an inner product of the Hessian with respect to, not the metric, you have to be careful, but like the metric restricted to the orthogonal to the radial direction, because the Hessian of R has a zero eigenvalue, so you can write it like that. And so you can use Cauchy-Schwarz inequality. And it will tell you that the Hessian of R squared is bigger than 1 over n minus 1 times Laplacian of R squared. Okay. And now, if we use, if we assume now that we have a lower bound on the Ricci curvature, then we will get that, for instance, that Ricci is greater than n minus 1k, which is the usual normalization. Like if you want to compare to the sphere, you would take k equal 1, and to compare to the hyperbolic space, you would take k equal minus 1. Then this equation gives you an inequality, which is very useful, which will be the following. So dr of the Laplacian of R plus 1 over n minus 1 Laplacian of R squared plus n minus 1 k is less than 0, if I'm not mistaken. Really? Okay, I guess. So yeah. Okay, so if we compare to yesterday's lecture, we have one big advantage here. Something is very simpler, is that we have a scalar differential inequality instead of a matrix one. However, we did disuse of the Cauchy-Schwarz inequality works only in one direction. You can control the Laplacian in terms of the Hessian, but you cannot control the Hessian in terms of the Laplacian alone. That's not possible. So this is a hint that in negative Ricci curvature or Ricci curvature bounded from above, you won't get very much result, especially with only that bound. With two-sided bounds on the Ricci curvature, you can say some things, but with only an upper bound on the Ricci curvature, at least in a qualitative topological way, you cannot say anything. Like and this is exemplified by Locam's results on manifold with negative Ricci curvature. Wouldn't work with Ricci less than n minus 1k. And yeah, just for general culture. So Locam proved that any mn with n greater than 3 compact as a metric with negative Ricci curvature. Okay. So negative Ricci curvature cannot have strong topological, cannot have any topological assumption, and those comparison geometry theorem, we didn't do much about it, but I guess if you will see in the lecture by Philippe, for instance, that they do have topological implications. So it's a hint that we cannot do comparison geometry with an upper bound on the Ricci curvature alone. Okay. So, but now we can try to integrate that along geodesics through a point. Like if you pick R, so studying this differential inequality, you can get, oh yeah, I have it in my notes. Maybe let's just not spend too much time writing that out. Just copy paste it. Okay. Right? Here. Okay, so this is the Laplacian comparison theorem for the distance function. And so it tells you that when you have a lower bound on the Ricci curvature, then you get, at least outside of the cut locus and outside of the point where the distance to a point is not smooth, you get that kind of inequality. like the Laplacian of R is less than n minus 1, this kind of generalized cotangent. And maybe it will be enough for the rest of the lecture just to focus on that case, which is just that it's less than n minus 1 over R, which is what it is in the Euclidean case, if we have a non-negative Ricci curvature. So, and the thing is just to try to solve this ODE and to compare the solution. So you have an inequality for Laplacian R. You look at solution of u prime plus 1 over n minus 1 u squared plus n minus 1 k equal to 0, and then you do a comparison. Metric, yeah. Sorry, trying to not spend too much time writing everything out, but if things are not clear, yeah, you should ask question, definitely. Okay, so and here, so I won't go too much into the details here, but and it's a little more complicated, though it's okay, I guess. This estimate holds in a weak sense on m minus p. So at p, you cannot get any upper bound on the Laplacian because it's basically like the absolute value. You cannot get any meaningful upper bound on the second derivative of the absolute value at the origin. But on the cut locus, actually, it goes the other direction. Like, in a way, it will look more concave than convex. So you can get an upper bound on this Laplacian. And yeah, so you can get it either in distribution sense or in barrier sense. And this is actually very useful. And same old one for the comparison theorem for non-negative sectional curvature. It has counterparts on the cut locus in a weak sense. Okay, so I did prove in some old notes of mine the comparison in distribution sense. For the comparison in barrier sense, you can look at. Oh yeah, no, I did prove it quickly also. So you can look in the notes if you want to learn more about that. But for a first approach, maybe acting as if everything is smooth, even though it's not the case, is a good way to get a feel of what's going on. Okay. So maybe an application of that. The first application, that probably a theorem that you encountered in your first Riemannian geometry lectures. So Meyer theorem. So if MNG has, let's say, has more Ricci curvature than the sphere, and is complete, then what? Then the diameter of MNG is less than the diameter of the sphere, and is less than pi. So this might be one of the easiest comparison geometry theorem. Like, if I'm more curved than the sphere, then my diameter is less than the diameter of the sphere. Okay, and so how do you prove that? So we can argue by contradiction. Maybe it's more clear, though it's not strictly necessary. So assume that you have 2 points, P and Q, in M, such that the distance from P to Q is greater than pi. So let gamma, we'll sometimes write like segments for any minimizing or some minimizing geodesic between P and Q. If there are multiple, I just pick one. So the length of gamma is equal to the distance between P and Q. And the Laplacian of, so yeah, of this function will be less than, okay, k equal 1 here. So 1, so cotangent of R, that's, oh, n minus 1 cotangent of R. And yeah. And this goes to minus infinity, or cotangent of, yeah, okay, let me explain. So I'm evaluating that at gamma of t. So this Laplacian of the distance function, you can look at it at gamma of t. And since my, so I take my geodesic parameterized by arc length. And so I have this thing. And I know that the distance function will be smooth in the inside of any minimizing geodesic. And so I have my minimizing geodesic here. So I know that it's smooth on the whole of gamma. So D cannot be smooth for some t inside, so between, let's say, so this goes to minus infinity as t goes to pi, between pi and yeah, the distance between p and q, which was supposed to be, and since these are interior points of the, cannot be smooth at gamma of t for some t inside this interval. And so that's a contradiction, because inside the minimizing geodesic from P, the distance function has to be smooth in the interior of any minimizing geodesic. Distance from the endpoint has to be smooth. Okay. So now let's go to something which will tie in nicely, I guess, with Gilles' lecture. So another application, famous application, is the Bishop-Gromov theorem. Okay, so we said that the Ricci curvature did control the evolution of the mean curvature of distance hypersurfaces, or we might as well, if we consider like distance to one point, of distance spheres. And we know that the mean curvature of an hypersurface controls the variation of the area of surrounding what do I want to say? Of surrounding hypersurfaces or spheres. So this will give us something interesting. Okay. So fix P in M. M as a Riemannian metric with Ricci greater than n minus 1, okay? And also set A of P and R to be the n minus 1 dimensional volume of the sphere with respect to the metric G, centered at P and of radius R. Okay? And let AK of R be the volume of the sphere of radius, so inside the space form of constant curvature kappa, K, who cares, centered at, let's say, 0, or some point, any point, I guess. And of radius R. Okay. So we know that the sectional, so we have some control on the mean curvature of those APR. So we have some control about how this APR behaves with respect to R. So let's write it down. So yeah, consider R also as the distance function from P to some point, and we want to compute the derivative of this area of distance spheres. And what is that? So this is the integral of the mean curvature. Yeah, maybe S, yeah, PR on SPR with respect to this d sigma. And so this will be, so this mean curvature is just the Laplacian of the distance function. So Laplacian of R, SPR, d sigma. And this is less than what it is inside the model space. So yeah, maybe let me. So what's that notation? I don't agree with the notation in my notes. That's bad. Maybe that's here. Yeah, okay. So basically, yeah, maybe I shouldn't add some free notation here, but so this is what I call MK of R. And what is that? A geometric way to see it is that it is the mean curvature of a radius R sphere in a space form of constant curvature K. Okay? Okay, let's continue here. And here, now, since I have this, so I can... So MK of R doesn't depend on the point of the sphere. So this here is equal to mk of R times the area of the sphere. Okay. Similarly, we can do the same computation in space form. And what this will give us is that what I called AK, which was just a function of R, has a derivative which is mk, which is equal to mk of R, AK of R. Okay. So now we can put all that together, and this is more or less the proof of this lemma, which says that if you have a curvature, maybe let me write it. So if Ricci is greater than n minus 1g, then this function for any p is non-increasing. So, and this has several consequences, and the proof is well, just compute the derivative and use what we said before. Okay. And yeah. So you will compute the derivative and see that it's negative. K is missing in the assumption. Yeah, you're right. Thank you. Yeah, I think I've switched off several times between writing lower bounds on the Ricci curvature in this form or with the metric. In any case, that says that the eigenvalues of the Ricci tensor are bigger than n minus 1k. I hope I didn't. I hope nobody freaked out because of that. Okay, so now we can actually integrate more or less that. It's a funny exercise, I will tell you, to get the Bishop-Gromov volume comparison. So here we have an area comparison estimate. Maybe an exercise. Okay, so I guess it's time to make a small poll. Okay, let's make a. See if you can get that. Thank you, Dell, if that's your name. So from this, what can you deduce something like that? So in for people on the chat, so in non-negative Ricci curvature, I'm asking whether distant spheres are smaller in area than in Rn. So there's one tool here that we haven't, there's one observation here to answer this question that we haven't given yet. Okay, we have 11 votes now, 12. Okay, that's you're doing better at voting than my undergrad did this semester. Thank you. So yeah, exercise. So what is the limit as r go to 0 of APR over AKR? So basically, you know that at small scales in a Riemannian manifold, the metric is Euclidean. So the area of distance spheres will be the same. So this limit is 1. Okay. But so we know that and we know that AP of R over AK of R is, so it's non-increasing. So let's say it's AP of epsilon over, it's big, no, in the other direction. Yep. So if epsilon is smaller than R, so now we can have epsilon going to 0. So that will give 1, and thus the area of distance spheres is less than the area of spheres in the model space. Okay. So it was 7 to say that it was false, and 5 to say that it was true that distance spheres had smaller area. Yeah. Anyway, if you haven't encountered that before, it's good exercise. Okay. So we can integrate, if we integrate that, we get between let's say 0 and big R, we get that the volume, the Riemannian volume of the ball centered at P of radius R is less than Vk of R, which would be the volume like of a ball in the model space. So this tells us that lower Ricci curvature bounds gives upper bound on the size of stuff, on the area, the diameter, the volume. What's more surprising and false actually is that you can get upper bounds. You can get also lower bounds on volumes with a lower bound on the Ricci curvature and a bound on the diameter. We'll see that afterwards, and it's a consequence of the following theorem. So which tells you that, so which is the Bishop-Gromov inequality. And once again, it will be stated as a monotonicity of some functions. Maybe you have already. I couldn't attend Felix Schulze lecture yesterday, but often in geometry, in geometric analysis, like monotone quantities are very important. Like for mean curvature flow, you have some kind of entropy, which are monotone and stuff like that. Here, this will be this volume ratio. Once again, mng with Ricci greater than n-1 kg, then this function, like Riemannian volume of balls, the ratio over this Riemannian volume of balls in the model space is once again non-increasing. The proof could actually make like maybe for a calculus class a nice exercise. So this boils down to the following observation. Like if you want to challenge undergrads, first year undergrads, I guess that's a nice way to do it. Assume f and g are positive function, and that f over g is smooth. Everybody is smooth, and that f over g is non-increasing. Then R maps to integral from 0 to R of say f of s ds g of s ds is also non-increasing. The proof is just like computing the derivative and trying to write it in a way that that makes use of the assumption on the fact that f over g is non-increasing. So yeah, so I will leave that as an exercise. It's written in the note. Okay, and now how does it give? So a corollary of that. Okay. So yeah, before I'm not sure what the statement of the corollary is anymore, so let me prove it and then I'll give you the statement. So we have that so volume of balls no, P. Oh, sorry, let me give a P. So that was I was telling you, it's how to get from the Bishop-Gromov inequality a lower bound on the volume of balls. This is what's called non-collapsing condition, which is very useful. Okay, so let's assume, so we write the fact that this function is non-decreasing. Yeah. No, that's a bad idea. We'll move that here. Okay. So BGP big R over VK of big R. Okay. And so this way I get an upper bound, but which depends on big R. So assume R is equal to D, which I denote by the diameter of MNG. Yeah. Sorry. Then that will tell you that the volume with respect to G of BGPR will be bigger than, so if R is equal to the diameter, and maybe that's a bit overkill, maybe you can do better, but that's not a big deal. But here we get the volume of M Vk of D times Vk of R. So the corollary is that control on, so given a lower bound on the Ricci curvature, control of the diameter and the volume gives a control on the volume of small balls. Which is very useful. And let's see an instance of where it's very useful. Actually, yeah. What time is it? I wanted to speak a little bit about the splitting theorem. Okay, so I will just state it. The application is Gromov's precompactness theorem. So in the first lecture, I stated that to have compactness in Gromov Hausdorff topology, you need to have the existence of an n for each epsilon, such that there is an epsilon network with at most n point. And actually, with this, you have yeah. With this, you have a control on the size of the balls, and this control will tell you by an argument that I won't repeat that you can find small epsilon network. So, and you can get the following theorem. Maybe I'll just copy paste the statement. Okay, so if you have a sequence of pointed complete Riemannian manifolds, so which is the non-compact case, which might be the most useful, with Ricci curvature with fixed dimension or dimension bounded above, it's not a big deal. Then there is a Gromov Hausdorff converging subsequence. Okay. Okay, now let's move on to the splitting theorem. But I will take like a 2-minute break, like it's getting very hot. I need to drink a lot of water. I hope it's okay so far. And so we will give the statement and the proof of the splitting theorem, which is one of the biggest tools in the study of non-negative Ricci curvature, and especially when you try to have Normal splitting theorem, it becomes very useful. Okay, so we are coming back in 5 minutes.
Okay.
Okay, I'm back. So now let's move on to the Gromov splitting theorem. So first, let's give a definition. Two definition. So array is a map from 0 plus infinity. I think we've already used that term in one of the lecture yesterday. To M such that so it's a minimizing geodesic on every subinterval, so which can be deduced from that. So the distance from C of 0 to C of t is equal to t, and a line more or less the same thing, but such that like the distance from C of s to C of t is equal to t minus s in every direction. Okay, so maybe to see if you get if you have a feel of this definition. If C Okay, so the question is the following. So assume you have a geodesic, which you don't know is a line, but you know that on R plus, so for positive times it is a ray, and for negative times it is a ray. Is it a line? Okay, I have 3 votes so far. And all of them are correct. Great. Okay, yeah, we have 8 votes. Let me give you the answer. The answer is no. How to see that? Well, consider some like cylinder capped off at one end. Then if you start from the tip of this surface, this will be a ray, and this will be a ray too. However, the union of both is not really minimizing in every subinterval, because if you take 2 points here, like, then the shortest path is here. So it's not minimizing as a geodesic from R to M, even though it's minimizing on R plus and on R minus, and on R minus, or depending on how you parameterize it. Okay, now let's give the statement of the theorem. It's Gromov splitting theorem. So if M and G has non-negative Ricci curvature, is complete, I always assume completeness, and has a line. So basically it's a limiting case of the Myers theorem. We know that Myers theorem tells us that when you have Ricci curvature bigger than something positive, then the diameter is finite. And having a line in some way It's like having infinite diameter, like you have an infinitely long geodesic in both directions. And so if you have a non-negative Ricci curvature and a line, then we say that M split. So Mn is diffeomorphic to some lower dimensional, yeah. Or maybe I'll put the R factor in front. R times n minus 1 with a metric, with a product metric. dr squared plus, let's call that Gn. And Gn has non-negative Ricci curvature too. And you can actually play, like if you have several lines independent in some sense, then you can split extra R factors. And this is a very useful tool in the analysis of non-negative Ricci curvature. Okay, so to prove such a theorem, we need a way to recognize that, but actually we do have one. And this will be crucial here. If R is a distance function, it's not strictly necessary, but this will be our setting. So we saw that yeah, there's a factor 1 out somewhere, but that so we have seen yesterday that the metric can be split into a factor in the radial direction and a metric on the hypersurfaces. And we saw that the Lie derivative of those metric on the hypersurfaces is equal to twice the Hessian of the distance function. So if the Hessian of R is equal to 0, then GR is equal to G naught, and M is a product. This is actually is this split? Yes, this is an isometric splitting. So here this twiddle is an isometric. So thanks Chunming and Dimitri. Okay. And yeah, this is an isometric because we have built a product metric here of one flat factor R and something fixed. Okay, so now we need to find the distance function which has vanishing Hessian. Okay, so how do we do that? So, okay. So first we will use just a ray and see what's going on with some special function. Assume C is a ray and set B sub t to be equal to the distance from C of t minus t. Okay, so this is a function. So B is this function bt are one, each bt is one Lipschitz. because distance functions are one Lipschitz. And more or less, the Laplacian of Bt by the non-negativity of the Ricci curvature is less than n-1 over distance to C of t. Okay. What we also have is that if I compute Bt at some point x, so this is d of x C of t minus t. I could now use the triangle inequality to insert what's going on at C of S. No, C of S, C of t, stupid. Minus t. And so this will be equal to d of x C of S. And this is S minus t since C is a ray. This guy here, it's S minus t. Here I use that C is a ray. And so it will be S minus or t minus S. Yeah, t is bigger than S. Assume t is bigger than S. So this will be t minus S. And t minus S. Yeah. So I will get that. And this will be Bs of x. Okay. So it tells us that t maps to Bt of x for every x is decreasing or non-increasing. Moreover, it's easy to see, so exercise maybe. For every x, Bt of x is bounded below. Hence, it has a limit as t goes to infinity. So n set b of x is equal to the limit as t go to infinity of those bt, so that I can write in full maybe. So the definition is that b is what is called the Boozman function associated to ray. They're also very useful. So to get the existence, we only use the triangle inequality. So this has nothing to do with non-negative Ricci curvature. Yeah, the fixed part has non-negative Ricci curvature. Christina. Yeah, that was 5 minutes ago. Sorry, I lost track of the chat. Yeah, maybe I should add that in the statement here. The Ricci curvature of n is also non-negative. Okay, so what can we do with that? When we have a line, we get two Boozman functions for free. So now let's see be a line. And let C plus to be the restriction of C to 0 plus infinity, C minus be the restriction of C to Oh, yeah. Yeah, maybe I'll write it. Yeah, I need to change the orientation, so maybe let's write it in full. Okay. So, what can we say about those two functions? So, I have b plus and b minus are the associated Boozman function. So from each, so we have our, it's pretty hard to draw something about the, to illustrate the proof, because you want to, and we have like this line here. That we split into like c plus of t here, c minus of t in that direction. Okay. Okay, now so I define a new function from these two Boozman function. B plus plus b minus. And I will note the following stuff, which again doesn't use anything about the Ricci curvature. Just a consequence of the triangle inequality. Yeah, maybe let's write that. So b plus. So u of x, you can write it as a limit as t goes to infinity of the distance to c of t plus the distance to c of minus t minus 2t. Basically what that, so, and yeah, okay. Let's leave that for the moment. So by the triangle inequality, we have that u is non-negative, and if x is equal to some c of t naught, then, and if t is bigger than t naught, then d of x c of t plus d of x c of minus t minus 2t will be equal, since we have a array, to here we have t naught minus t. Basically here what I'm doing is that I'm picking some point here, some c of t naught here, and then so the distance between here and here can be computed, since we are on a line, actually, not a ray here. So t naught minus t plus t naught minus t minus 2t, and this will be equal to 0. So we have non-negativity of u, and we also have that on any point of C, that U vanishes on C. Now, let's prove a lemma from this. And so far, we haven't used the non-negative Ricci curvature. Okay. So the lemma is that U is identically 0 on M. Okay. Okay, so how do you prove that? Okay, so I haven't used non-negative Ricci, so if let's be explicit with that. This is here that we use non-negative Ricci curvature. So how do we prove that? Well, now we need to use Ricci curvature. So recall that U is equal to B plus B minus, and so the Laplacian of B plus, oh, I have to be careful with my pluses and my t. So if I take B plus of t to be a Guzman function at a finite scale before I take the limit, so we saw that it was less than, not 1, but n minus 1. Distance from C of t. And at every x, or for any x in a compact set, this goes to 0, say uniformly on compact sets. So what that tells you is that in a weak sense, for instance, in barrier sense, the Laplacian of B plus, this is the limit as t goes to infinity. The Laplacian of B plus is less than 0. And so we can do the same thing with B minus. So we have the Laplacian of U, which is Laplacian of B plus B minus is less than 0. And so we have a superharmonic function which attains its minimum, then it is a maximum principle in harmonic function that tells you that it has to be constant. So the maximum principle in that context, so delta U less than 0, U of some point equal to 0 and U non-negative implies that U is constant equal to 0 on M. Okay. Now, we are still not done, but we are almost done. So, observation now. So B plus is superharmonic. And B minus is also superharmonic. But since U is equal to 0, B plus is equal to minus B minus, and B plus is a harmonic function. Okay? In particular, So being harmonic in a weak sense and being smooth is the same. So B plus is smooth. So once we're here, we don't have to care about smoothness and weak derivatives and so on. Okay, now let's prove two things and we will be done. Let's prove that the gradient of B plus is constant and equal to 1. So this is not complicated. First, as a limit of one Lipschitz function, B plus is one Lipschitz. Since it is smooth, using the smoothness of B plus, the gradient of B plus is less than 1. And moreover, so if you compute B plus of C of t, that's more or less the same computation that we did here. You will see that it is minus t. Okay, so there's a point where this gradient, so in particular, gradient of B plus at the point C of t as norm 1. And now I will use Bochner formula. So in that case, so when you see the interest of that here, I don't know for now that B is a distance function. So this is important to know the Bochner formula for functions which are not known to be distance function. Hn of B squared plus Ricci of gradient B plus gradient B plus. Oh, sorry. This is unreadable. So yeah, maybe let's just skip. So this is a corollary of the Bochner formula. Using the harmonic assumption, so this gradient of Laplace B inner product with gradient B is gone. And this Ricci curvature assumption, which allows us to get rid of the curvature term. So hence now gradient of B plus squared is subharmonic and attains its maximum because of that. So gradient of B plus is constant equal to 1. So this is a distance function now. And okay. But yeah, now second lemma, and this will be the end of the talk. Hn of B plus is equal to 0. Well, now the answer is here. So since B plus is a distance function, the Laplacian of B plus squared is equal to 0. And we already said that this was bigger than the Hn of B plus squared. So check. Okay, so we considered those Boozman functions, which Boozman functions should be thought of kind of distance from the infinity given by the ray it's defined with. And here we see that they were actually distance function, which need not be the case. Like this maximum principle here was pivotal in proving that. And we showed with the Ricci curvature hypothesis that there were distance function with zero Hessian, and that gives us the splitting that we wanted. Okay, it's 10:31. That's all I had to say on Ricci curvature, comparison geometry for Ricci curvature. Tomorrow, in preparation for Professor Bamler's talk in next week, we will do a quick intro to the basics of Ricci flow, maybe talking about Hamilton's first results and a little bit of detail so that you see what are the techniques involved. Okay. Thank you all for your attention. I remain online for a couple of minutes if there are questions.
Okay.